Thank you. So I was told to keep this brief. I'll do my best. Anyway, you all have seen the calibration phantoms. I think you're aware that, this is a low-cost device you put in your scanner. It started off as Scotch tape, and we upgraded everything to precision grade aeronautical plastics. But basically, we give back a report to the site with whether you passed or failed in terms of fundamental properties of an image acquisition system. In addition, we give all of those metrics, 3D resolution, noise, linearity, bunch of other things. So what that means is we get a mathematical model of the acquisition system, a first order mathematical model of the acquisition system. And as you probably are more aware than I am, if you have a mathematical model, you can do a lot of things with it. Like when Claudia called me up a couple of days ago and said, can you tell me what scanners are going to be doing in terms of resolution in the next 10 years? And I just went back to our 20 years of data on this, extrapolated 10 more years, and I gave her, and I simulated some images. That's because we had a mathematical model. Could she have asked, will I be able to see a 0.5 millimeter vessel? Yeah, she could have. And we could have said kind of what that would have looked like and how much more we could have gotten out of the image because of it. So it's a very powerful thing. Again, it's based on fundamentals. We've been evolving the phantoms. There's now a new phantom in the back, which is all plastic actually now. And we get this information from isocenter out to periphery. As Ilya showed earlier, if you have that information, you can run protocols through it and optimize your resolution versus noise versus other things. And it should, from fundamental principles, should give you better measurements of certain objects. And we actually showed that. And then Mevis went and took the data that GE generated and they ran it through their software. And guess what happened? They saw the same, not the same magnitude, same direction, same approximately what they got around 30% improvement, and GE saw about a 50% improvement. So very exciting stuff. I was asked to give 2 real down-to-earth use cases. So here we go. First, so most sites have multiple scanners, and not all scanners are operating at the same time. So what happens? In real-world practice, probably on a given year, there's a few people who are going to get sent to a different scanner than they were scanned on last time. Now, that could either be the exact same scanner and scanner model and everything's identical, or it could be a different model, a different recon kernel, a different everything. And of course, the site has a responsibility to try and keep those two scans, those 2 protocols as similar as possible. Now, if you were going to do that, what would you want to do it based on? If it were me, I would use fundamentals, resolution, noise, linearity, etc. So that's something that we advise people to do, is to baseline and understand each scanner in their set of scanners they use for screening, even the ones that they're going to use from outside. Sometimes you get scans from outside. Well, it's better to know what you're doing. What kind of quality are you getting? Because I'll tell you one thing, there are scanners out there that can do some terrible things. And if you get one of those, you might draw the wrong conclusion. So that's one use case. The second one is similar, but we're all taking care, we're talking about taking care of millions and millions of participants around the world. And every 3 years to 5 years, a scanner is going to be replaced, right? How do you guarantee that that scanner is doing the same thing that the previous scanner did? And if you see a change in a nodule, on the old scanner and now on a new scanner, is that a real change or is that just because you switched? Again, having a little more information at your fingertips, like, you know, hey, this scanner is very different, or this is dead on, exactly the same. We didn't change at all. And then you have to take into account scanner repairs, replacements, software updates, and even things that happen that you don't even know about. Your scanner folks came in and they adjusted something for some reason. They don't even have to tell you. So those are the two main use cases. I'll go add a third. If you're running a study, wouldn't you want to know how you're, wouldn't you want to capture how you did the study? Wouldn't you want to know the fundamentals of your acquisition system, so that when you go do a next study, you can compare it. Study meaning in the bigger sense, not for an individual or population. So we've been showing the evidence for the importance of CT image quality for decades, as Jim said. This shows that if you focus on acquiring high quality data, you can see differences that you wouldn't have seen before. So on the right, those two bars are the sensitivity and specificity of malignancy assignment. And it gets better when you have higher quality data. This is a I-ELCAP paper with I-ELCAP that I helped with a long time ago. And then here's GE and the result from GE. And I mentioned MEVIS as well. And then we've been showing that if we know a location of a nodule, and we now have massive databases of image quality and what the result is, we can target an acquisition and even customize a protocol to make sure we get the highest quality data. So on the left is what a 512 by 512 matrix view of a star-shaped object is. I 3D printed this. This is tiny. It's like the center of it's 6 millimeters by 3.6 by 3.6. So each of the spires coming out of it is only a few millimeters long. But if we know it's there, we can modify the modify the protocol and get an image on the right, comparable image on the right. So obviously you can measure those much better.